Okay, good morning, everyone. So it's 8 o'clock in the morning. So let's start. So thank you so much for joining us on the fourth lecture of the Sustainability Lecture Series. So the Sustainability Lecture Series is an initiative of De La Salle University in cooperation with the International Association of De La Salle Universities. These monthly talks are meant to engage the global Lasallian community in responding to the UN Sustainable Development Goals and Pope Francis Laudato Si encyclicals. The LaSalle Sustainability Lecture Series is being organized by De La Salle University Manila in cooperation with the International Association of LaSalle University and in coordination with the Center for Engineering and Sustainable Development Research. So without further ado, I'd like to request the Director of the Center of Engineering and Sustainable Development Research to introduce our speaker for today. Yes, Dr. Kulaba, kindly introduce our speaker.
Good morning, everyone, and good evening or good afternoon in the many parts of the world. Thank you very much, Dr. Kathleen Aviso. This is, really a very welcome morning to everyone in the Philippines, in spite of these very difficult situations that we are in. We are still able to provide this series of lectures to our wide audience, primarily to really encourage discourse on the issue related to sustainable development in our countries. The This morning we are joined by our distinguished guests, and I would like to acknowledge the presence here in our virtual environment. Chancellor Emeritus of De La Salle University, Carmelita Quebenco. We have seen, some of our Lasallian brothers all over the world. Of course, we have Brother Joe Scheiter, Brother Francois, Brother Jock. I don't, and probably there are a host of other brothers not seen on the list, but nonetheless, to our colleagues at De La Salle University, members of the scientific community, from the many different universities and institutions, our guests from other countries and collaborators of our speaker. Uh, Again, a pleasant day to everyone. The Center for Engineering and Sustainable Development Research was established back in 2013, and it was envisioned to become a center of excellence in engineering research and technology innovations. It aims to make significant contributions to growing scientific knowledge in engineering and technology. It has engaged in experimental research and modeling of industrial systems and development of innovative processes and products that has led to the utilization of sustainable technologies. It has facilitated the effective transfer of the many technologies from the academic research community to industry and society in the pursuit of sustainable development. To date, over 1,600 publications in various sustainability-related researches have been published in international journals by our top research scientists and fellows in the center. And this morning, we have one of the most distinguished scientists and fellow of the center, and is going to be our speaker for this particular series. He is a professor of chemical engineering and university fellow at De La Salle University, and currently our vice chancellor for research and innovation. With over 500 publications and over 8,000 citations with an H index of 48 in Scopus. He is a member of the Philippine National Academy of Science and Technology, and earned his degrees in chemical engineering and a PhD in mechanical engineering at De La Salle University. A multiple scientific awardee from the Department of Science and Technology, from the National Academy, the National Research Council of the Philippines, Philippine Association for the Advancement of Science, our alumni, and the Philippine American Academy of Science and Engineering. He is the editor in the Process Integration and Optimization for Sustainability, an associate editor of Sustainable Production and Consumption, the Cleaner Engineering and Technology, member of the various editorial boards of Clean Technologies and Environmental Policy, as well as the International Journal of Supply Chain and Operations Resilience, author of Process Integration Approaches to Planning Carbon Management Networks, Models for Sustainable Industrial Systems, and also the editor of Recent Advances in Sustainable Process Design and Optimization, as well as the Process Design Strategies for Biomass Conversion. His areas of interest include process systems engineering, process integration, life cycle assessment, input-output modeling, as well as process graph. In 2019, his work has been featured in UK's IChemE's the Engineer magazine, and 3 articles have been listed among the 31 publications featured, in IChemE climate change collection. Our distinguished speaker belongs to the Stanford list of the top 2% of researchers across all fields.
Oh my God.
The high ranking, in fact, within the top 5 on process integration in the Google Scholar, and ranks top 5 in the carbon management, also in the Google Scholar, and within the top 20 a scholar in the process systems engineering. And recently has been in the hot list of Reuters top 1,000 climate scientists. Ladies and gentlemen, it is my pleasure and honor to present to you Professor Dr. Raymond Gerard Artan. Raymond.
Thank you very much. It's always an honor as well if you're introduced by your former PhD advisor. Brings back memories, good memories of old times. But it also means we're getting older. Let me begin by sharing my screen. Good morning, friends and colleagues from different parts of the world. I'm happy to give a talk for about the next 30 minutes entitled Engineering Terrestrial Carbon Drawdown. And I'm sure some of you may have found something grammatically odd about the title, but that was by design. I use the word engineering here as a verb, and to engineer something means essentially that it's not a passive activity. You're trying to manipulate or intervene with a particular goal in mind. So the talk is about how to engineer terrestrial carbon drawdown. This is linked to the 13th Sustainable Development Goal, which is climate action. And it is also peripherally linked to the second SDG, which is zero hunger, as you'll see as I progress through my talk. Of course, I'm representing De La Salle University here, where I've worked for a quarter of a century already. It's notable that in 2015, we updated our mission vision and inserted the phrase attuned to a sustainable earth, which is in keeping with our university colors. We've used green as our university colors for almost the entire life of the institution. So it's a few years ago, we decided to really become the Green University as well. So I'll begin my talk shortly, and I'll begin with a quote from a paper which was written 44 years ago by Freeman Dyson, who wrote that should there ever be a future climate emergency, then it should be physically possible to remove carbon dioxide from the atmosphere very rapidly just by using photosynthesis. And this was, let's keep in mind, in 1977, climate change was far off in the distant horizon in as far as public discourse was concerned. But it's interesting that Freeman Dyson was able to see that far into the future. And fast forward to 2021, here we are actually facing the very climate emergency that he envisioned. So my talk is organized as follows, and I understand that we have a general non-engineering audience, so I will deliver it in a way that's a lot more accessible than my normal delivery. So I'll begin by discussing negative emissions technologies and climate change. As I mentioned, all right, we seem to be, all right, we seem to be having some technical difficulties, but all right. Once again, the 13th SDG is climate action, which includes both mitigation of climate change and adaptation to climate change, which is already occurring.
Engineering ko eh. Ni-register kita.
All right, hang on, I'm having technical difficulties. I'll stop sharing and then reshare that. And let me explain very briefly what climate change is all about. The fundamental problem is that human activity is pouring large quantities of greenhouse gases into the atmosphere. And for example, the current figure is approximately 40 billion tons of carbon dioxide per year, and it's been on an upward trajectory ever since civilization began. Now, this report, which was released by the IPCC in 2018, actually outlines a roadmap for us to keep warming by the end of the century, by 2100, to 1.5 degrees Celsius temperature rise relative to pre-industrial times. And the problem with climate change is that it's a bit like driving a car. If you switch off your engine, your car is going to have momentum and it's still going to continue rolling forwards. And because we pumped so much greenhouse gas into the atmosphere, even if we were to stop emitting greenhouse gases, say next year, it would still take many decades for the momentum of climate change, so to speak, for that to slow down to appreciable levels. And what that means is if we're targeting to have controlled temperature rise 80 years from now, by 2100, we actually need action decades ahead of time to allow for the time lag to catch up. And this IPCC report notes that we actually need to draw down the carbon emissions from what has been for so long an upward trajectory, and within the span of one human generation, by 2050 to draw this down to zero, which is really a tough task, both technologically and politically.
And the seminar, again, from the LSU, the one that I also told you.
Okay. Nevertheless, there has been some traction recently. So that was the global picture, and we're seeing major economies throughout the world actually making commitments to this zero emissions bandwagon. For example, the European Union with the 20 plus states are really serious about this, and they're investing billions of euros into R&D and technology deployment to achieve this goal. Japan recently made an announcement. The UK, which is no longer part of the EU, has made a similar target. And it's quite significant. It's a very promising development that the largest source of carbon dioxide emissions in the world, China, has likewise made a similar commitment, although their target is to hit zero emissions by 2060, which is still fairly ambitious and still quite beneficial for the entire world if they make serious gains towards such targets. So that is as far as the political climate is concerned. It's something that we should be happy with. How do you actually do it? How do you engineer the political decisions? Well, it turns out, according to this paper by Hazeldine and colleagues 3 years ago, to get to net zero emissions by the middle of the century, not only do we need to stop emissions that are going into the atmosphere, we actually need to begin removing the emissions that were historically put there in past generations. So we need to reverse the flow of carbon dioxide and greenhouse gases, not into the atmosphere, but from the atmosphere. And this is known as either carbon dioxide removal, if you look at IPCC documents, or in the scientific literature, it's known as negative emissions techniques or technologies, or NETs. I think we should be able to understand what's going on if we have at least a picture of the carbon cycle. The amount of carbon on the planet is essentially fixed, but there's a distribution. Some of that is in the atmosphere where we don't want it. Some of it is terrestrial, so it's in biomass, in living things or in things that were recently alive. Some of it is underground in fossil fuels, which used to be living things. And some of it is in the water in our seas and oceans, either as minerals that are dissolved or deposited, and also in living things. So the total amount is fixed. And what's been happening for most of human civilization is we've been transferring carbon from, especially from fossil fuels and from living biomass. And by using these resources, we transfer a lot of it at a very fast rate into the atmosphere. And that's like putting a blanket around the planet, which is what's causing the warming. So what we need to do is, if we understand the cycle, we should be able to manipulate parts of the cycle which are favorable to our goal and engineer those parts of the cycle so that they help control climate change. And in my talk, I'll zoom in particular on two things. Number one is known as biochar application. And let me begin with soil. If you take soil from your lawn or from a forest, a lot of the soil that you're holding actually contains plenty of carbon in the form of microbes, in the form of dead living tissue, dead tissue, which came from vegetation, or which came from animals that died. So the point is, soil actually contains plenty of carbon. And if you take a typical forest, for instance, there is in fact a lot more carbon in the soil than there is above ground in the trees and living vegetation. So one of the things we could do is, could we engineer a way to increase the amount of carbon that is stored in soil and lock it up in a form that's very stable, that doesn't rot? The problem, of course, is if it rots, then you get carbon release into the atmosphere. So if we could lock up the carbon in the soil, then we could actually help stabilize this part of the carbon cycle. And one of the ways we could do it is biochar application. I'll more on this later, except to say that biochar is no different from the charcoal that you would use to grill your food. It's just that when you say charcoal, you normally intend to use it as fuel. But if you say biochar, you grind up your charcoal into a fine powder, and then you mix it with soil as you would compost. And that really locks up the carbon in very stable form in soil. Now, the other part of the carbon cycle which we can enhance is what is known as mineral weathering. Now, when there's rain, rainwater actually always contains a tiny bit of dissolved carbon dioxide, and that solution is known as carbonic acid, and that's very slightly acidic, but it actually reacts with rocks and minerals. And what happens is when you hit slightly alkaline rocks, you get the water that runs off contains bicarbonate ions. And if, just to simplify that, if you take baking soda and dissolve it in water, what you have are bicarbonate ions. So that is a naturally occurring reaction between rainwater and a lot of minerals. The water eventually runs off into rivers and eventually ends up in the sea, where the carbon that was originally in the atmosphere is entrapped for a large number of years, virtually permanently. If you look at human timescales, it's entrapped as dissolved carbon dioxide, rather dissolved carbon in the bicarbonate in the sea. So this is a naturally occurring process, just like the soil biomass. And if we can enhance or accelerate this process, we can actually begin drawing down carbon from the atmosphere to offset some of the emissions that humans are generating. So let's have an overview of these two techniques and look at some of the key results that scientists have reported throughout the world from the past couple of decades. If you look at biochar, which would look something like this, you know that essentially it looks like charcoal which has been ground down to a finer to fine grains. Wolf and colleagues in 2010 estimated that if you were to do this at scale throughout the entire planet at the maximum rate possible, until the end of the century, you'd get over 100 gigatons of negative emissions. In other words, 100 billion tons of carbon dioxide could be removed from the atmosphere just by photosynthesis, growing plants and turning those plants into charcoal, which does not return to the atmosphere for as long as you don't burn it. So that was the estimate reported by Wolf and colleagues. Now, a much more recent paper by Pete Smith and colleagues estimated the potential for enhanced weathering is even bigger. You can get 3 or 4 billion tons per year of drawdown if you were to enhance the weathering of rocks such as basalt, which is shown on screen. The lower picture would be basalt. This is the same kind of rock that is mixed with cement to make concrete or mixed with asphalt for tarmac. So it's a very abundant rock. If you could use it potentially for carbon drawdown, the potential is so huge. It's in the billions of tons per year. And this is really what we need, because recall from my earlier slide that the emissions that we're generating, the background emissions, are in the order of about 40 billion tons per year. So if we need climate change mitigation measures, they need to be at the scale of billions of tons per year, even begin to make a dent in the background emissions. What we do need to understand is that there is no such thing as a silver bullet. In other words, all of these technological solutions would have their own price tag, so to speak. And in the case of both biochar and enhanced weathering, we need to look at land footprint. We need to have land where we apply either the biochar or the crushed rock. And then we would need water, nutrient, energy, and we need to study what the implications are when we do this at the gigaton scale. There is an added bonus. If we pick the right sites for application of either the biochar or the powdered rocks, there may be beneficial effects on substandard soils. So that is why I mentioned that we have implications on farming productivity throughout the world if we're smart about matching where we apply these two techniques. All right, so let me move on to the second part of my talk, which is about my own field is process systems engineering and how we apply that for carbon management. And before I jump into my slides, let me point out something just to illustrate a point. The amount of hunger that occurs in the world today, or malnutrition, is actually far larger than what you would deduce looking at global food production. In other words, there's inequitable distribution of food throughout the planet. There are places where you have too much and places where there isn't enough. So what that tells us is having a potential, which is estimated at so many gigatons per year, doesn't mean that you can actually implement to the maximum potential. If we can't do it for something as basic as food, how are we going to be able to maximize the potential of carbon drawdown? And the reason for that is that there are driving forces at work in real life which prevent full utilization of potential. So for example, even for what is for the layperson seemingly the most obvious solution to climate change, which is afforestation and reforestation, this is actually still very controversial. Here are a couple of recent papers which contradict each other. In 2019, Bastin and colleagues did some simulations and estimated that if you take 1 billion hectares of land throughout the planet, which is about 15%, roughly about 15% of total land area, no, sorry, not 15%, something like 6 or 7% of total land area available. If you maximize reforestation potential, you could potentially sequester 200 gigatons, 200 billion tons of carbon during that period. But there were some critics who actually pointed out some flaws in their argument and said, I quote, "The claim that global tree restoration is our most effective climate change solution is simply incorrect, partly because if you have that maximum potential, there is no guarantee that that can be reached, because you need to ask yourself, is there going to be enough water to grow all those trees? And there's going to be competition with human need for the same water resources and such. So even for solutions that seem simple, the solutions actually are very seldom clear-cut. And this is where engineering comes in. And my own field, my own work has been about developing mathematical models so that we can model future systems in a way that we can squeeze out the maximum potential based on the characteristics of the system that we're analyzing. I won't go into any more detail. Of course, this is meant for a general audience, except that we're developing computational toolboxes. And in 2020, I wrote a paper with colleagues from Malaysia and India, where we wrote that averting a climate crisis will require nets at the scale of gigatons per year, but we must cope with resource limitations on their use. So that now brings us to an overview of some of the stuff I've done. First of all, let's see how we've done that for biochar for negative emissions. I have a couple of overview papers on this. One was written by my PhD student. We spoke of biochar and its place in the water, energy, food nexus. And much more recently, I wrote a paper on the technology that would be required to monitor implementing this on a large scale in the future. My first adventure in biochar production really began with the PhD work of a couple of students. This is an industrial plant that runs on biomass, so forget about all the details, except to say that all right, again, minor technical issue. Let me get back to my screen and all right, back to this. This plant can be configured to take biomass, and part of it becomes biochar, which would look something like this. If you commit to putting this in soil, we showed that this industrial plant would actually be generating a negative carbon footprint. So this is one industrial plant. How does that fit into a much larger system? Because in the future, when we start doing this, you would build multiple plants that are producing biochar. The question would be for the companies that make them, where would you build your plants? Where would you put them so that they're close enough to the application sites that it's economical to do this? And this is where we created models for what are known as carbon management networks, or CMNs. These are schematically shown in the middle of the screen, where the circles are the signify the plants where you make the biochar. The blocks on the right side show where you send the biochar and you put it in the soil. And just like if you were to look at a subway map from London or Tokyo, the subway maps look nothing like the cities that they actually represent. So these are just schematic representations that allow us to easily map how we match those biochar plants with the biochar application sites, which could be very large plantations or farms, where we're also trying to produce a carbon drawdown effect. Last year, I did this with some colleagues from the Philippines, and this is important to note because electricity generation in countries like the Philippines or in India or even China remains highly dependent on coal-fired power plants. And while we should not be building new coal-fired power plants, in my opinion, we need to make full use of those that are still in operation, because we need that electricity. So the strategy that we proposed in this paper was, if you have, for instance, 10 coal-fired power plants, option A would be you shut down one of them completely, you mothball that plant, and you build a replacement plant that runs on biomass, and you're able to maintain your production of electricity. But we also showed that there's a strategy known as biomass co-firing, where you retain those 10 power plants, keep them running, but you run them on a mixture of biomass and coal. And typically the limit might be 90% coal, and then you replace 10% of that with equivalent energy biomass. And the effect is the same. It's as if you shut down one entire coal-fired power plant and built a renewable energy plant in its place, except you've spread out the financial risk over 10 plants rather than a single one. Now, what we did was we took this one step further. Instead of replacing the coal directly with biomass, which could be straw, this could be rice hull, we examined the situation of using indirect co-firing, where we also produce excess biochar while generating electricity. And that excess biochar, we then send it, just as we did before, we send it to farms and we apply it to soil for the carbon drawdown effect. And this allows us to actually compound the reduction in carbon emissions. So it would be equivalent to not just shutting down one of the 10 coal-fired power plants, but shutting down maybe not quite double the effect, but there's an enhancement of the carbon reduction effect. And this is actually scalable in a country like the Philippines or India, which is developing and requires growing electricity production. And then later in 2020, I did this work with some colleagues from Malaysia. And in Malaysia, they make a lot of palm oil, which is a major global vegetable oil commodity. The problem is, for every ton of palm oil that you produce, you're also producing about 4 tons of waste biomass, which can be problematic to handle because there are different kinds of biomass and different potential markets for it. So we showed in our recent paper that one of the ways you could deal with this biomass is turn that into biochar, which locks up the carbon, and send the same biochar back into the plantations where the palm came from to begin with. So you're actually closing the carbon loop and utilizing some of the biomass effectively. And this can have significant carbon drawdown effect if done in countries like Malaysia, Indonesia, Nigeria, which are major palm oil producers. Okay, now let's switch gears a bit. I want to talk next about some of my recent work on enhanced weathering. I wrote a paper about the life cycle implications of enhanced weathering as a negative emissions technique earlier this year. I was actually interviewed in January in a podcast, which you can view. If you can stand my voice for another 60 minutes, you can watch this or listen to this podcast. And I discuss some of the implications of enhanced weathering carbon drawdown. But the work I've done in this area is a bit more limited. But likewise, the problem is, if we're looking at basalt or similar minerals, then these will come from quarries where you have dynamite to blast out some of the fragments. You want to then grind down the rocks down to the size of, eventually you need to bring it down to about 10 microns. And 10 microns is much, much finer, for example, than the size of the particles of cornstarch and flour. So you can imagine a lot of energy goes into the process of breaking down the rocks, which would be normally gravel like this, but get it down to essentially rock flour. And then you have to ship that dust via trucks to different application sites. And again, you would use it as a compost-like soil conditioning strategy. This is already being done for very acidic soils. You can add minerals that are slightly alkaline to bring up the pH so that you can use the soil for better agricultural production levels. So the problem again is, where do you source your rocks? Where do you build the crushing plants? And where do you ship the rocks for application to the lands, to the receiving lands? And what we developed are computer models that can allow us to do this either at minimum cost or maximum sequestration potential, or both. And here's one interesting work which we did with a colleague from Taiwan, where, among other things, Taiwan is a major producer of iron and steel. I believe 14th or 15th biggest in the world, even though Taiwan itself is such a small island economy. And we looked at the concept of circular economy. Can we use industrial waste as a way to manage carbon emissions? And in Taiwan, they have what are known as blast furnaces. This is where raw iron is produced. They have 2 large sites which actually contain multiple blast furnaces. And in the production of iron, you have what's called slag. This is essentially a mineral comprised mainly of silicate. So it really is chemically very similar to a lot of rocks that you would encounter in real life. And this is normally just stockpiled on site. And eventually it accumulates and becomes a disposal problem. Some of it can be used for cement production and such. But we examined what would happen if we use that blast furnace slag and we use it for enhanced weathering by applying the powdered slag to marginal lands all over Taiwan. And we set up a computer model This is a map of Taiwan, and you can see where the slag comes from and where it's eventually applied. And by doing this, just by using one kind of industrial waste, we showed that Taiwan can reduce emissions by almost 2 million tons per year of carbon dioxide. Now, this is still not gigaton scale, this is megaton scale, but bear in mind, this is just one country and just one kind of industrial waste. The problem is the cost is still a bit prohibitive. We estimate the cost to be about $170 per ton of carbon dioxide. That needs to be brought down to a benchmark level of $100 per ton for it to be economically viable. So there's still plenty of research to be done. Now, let me move to conclusions and further research prospects. We know that negative emissions will be part of the carbon management menu for the entire world in the coming decades, but there are issues that we need to deal with. Number one is techno-economic uncertainties. Many of these techniques are not yet proven at the gigaton scale, so we don't know exactly how much they'll cost and how effective they'll be. There may be unintended consequences or ripple effects, so we need scientists to be looking out for, scientists and researchers tend to treat their work as their babies, and you sort of, when you have a baby, it seems to be the most beautiful baby in the world, which probably isn't true. And that's the same thing with your own specializations. You tend to see only the good points and miss all of the potential pitfalls. So there needs to be a discussion on the unintended consequences that may occur and the ripple effects, natural resource limitations, including land, water, energy limitations. And again, it's easy to fixate on one particular technique if you're doing research on it. We need to understand the big picture. How do all of these techniques fit together? Because potentially, it's much more likely that we can manage climate change by a combination of a menu of different techniques rather than a single magic bullet. Then there's the issue of legal framework and social acceptability. For instance, in Manila, we still do have a controversial site where aesthetic beach enhancement by applying rocks on a strip of sand has met with a general public outcry. Now, that technique can actually be done with basalt if your objective is carbon sequestration, but as we've seen, there could be public resistance to such measures. And obviously the economics would always be part of the picture. Who's going to pay for carbon drawdown? Is there going to be a carbon tax or some kind of carbon trading regime to enforce this? But in conclusion, I think the most important points would be, number one, nets will be necessary to achieve net zero global emissions. Many countries are taking this seriously, so there is hope for our children and their children that we may be able to manage climate change after all. But we need a crystal ball to see into the future. And this is where computer models come into the picture. If you configure your models properly, you get something like an electronic or a virtual crystal ball. So you can make predictions about the future on how to engineer these techniques so that you can maximize the benefits and minimize the disadvantages and adverse effects. And finally, the models can help us understand how new technologies plug into the background system. And we need to understand that there's a whole technosphere that already exists. And every time you plug something in new, it affects the rest of the system. And very, very often these ripple effects are very difficult to imagine. And the human mind can only begin to imagine them with the aid of computer models that highlight specific effects. So that concludes my presentation. I just want to thank the various colleagues, current and former students, and collaborators who've helped with my work. And I'd like to thank funding agencies from the Philippines who've supported some of the work, including scholarships of past students. Okay, that concludes my talk. We'll be happy to take questions in the time that remains. But in the future, if you have questions, please feel free to email me as well. These are my contact details. Thank you and good morning, good evening, and good afternoon, wherever you happen to be.
Thank you very much for that, Raymond. Okay, we actually have a few questions in the chat, but for those of us who are watching on YouTube, unfortunately, I just checked the live chat feature has been disabled. It was because I labeled the video to be made for kids, and apparently Okay, live chat is not allowed when it's made for kids. All right, so let's go through some questions. So the first one comes from TG Jayanth. So if you add biomass to coal in power plants, aren't you adding the same carbon dioxide to the atmosphere? Why is that better than just coal-fired power generation?
All right. What needs to be done is to understand the concept of carbon neutrality and carbon neutrality in human timescales. And there's a distinct difference when you burn a fossil fuel like coal, which is that when you burn coal or when you burn petroleum or natural gas, the carbon throughout most of human history was previously in the ground. And now you're burning it and transferring it into the atmosphere. So that is a net transfer from a terrestrial compartment into the atmospheric compartment. When you burn biomass, the same biomass that you burned was very recently in the atmosphere and was actually taken, the carbon was taken out of the atmosphere via photosynthesis when the plant was growing. So when you burn that same biomass, all you're doing is returning the same carbon back into the atmosphere where it came from within a short time frame. And in principle, you can actually design a balanced system. This is known as, I forget the exact term, but you could have a balanced system where you have energy plantations and you have biomass power plants, which are perfectly balanced. So the trees are growing at just the right pace that you're burning the trees, cutting them down periodically and burning them. So you have a closed loop, a closed carbon neutral loop where there is photosynthetic carbon drawdown that is completely offset by carbon emissions from burning the biomass. So as long as it's balanced, you have what's called a carbon neutral system. So that's the basic reason why burning biomass is carbon neutral and burning fossil fuel is not.
Thanks for that. The next one comes from Elmar Villota. So, a quick question on the biomass co-firing. Is it via biomass fast pyrolysis or gasification? As far as I know, these power plants use either combustion or gasification, and we cannot expect significant char byproducts from these. I am wondering how much biochar, say in terms of percentage of the biomass input, is required to have a net effect, and strategies to come up with that amount. Another question, do you have work or related work that deals with a potential sustainable available biomass second generation non-food based that can be converted to biochar for the sole purpose of carbon sequestration?
All right, thank you for those questions. Now, just to clarify the first point, there are two major kinds of co-firing. One is direct co-firing, where you would take, but there are actually subcategories further within that. But what you can do is you can take a coal-fired power plant and take biomass, for example, straw, and then you reduce the size so that you can inject it into your combustors and replace a portion of your coal with that biomass. That's called direct co-firing, and that essentially offsets carbon only by displacing coal. Now, there's a second category which is known as indirect co-firing, where you could use an intermediate thermochemical process. So you don't burn the biomass itself. You pyrolyze your biomass so that you're producing biochar. But there's a byproduct when you do this. The byproduct would be the gaseous and liquid fractions, which would be combustible. And that fraction, which you would not be able to put in soil, is what you use for indirect co-firing. Now, you can calibrate this process, and of course, by changing process conditions, you can actually manipulate the biochar to biomass yield. But the point really is that you're not using up all of your biomass as fuel. You're using the liquid and gaseous fraction to displace some of your coal, and the solid fraction, which is your biochar, would then be what goes into the soil as a form of carbon sequestration. In the model that we generated, which, by the way, if you're interested in technical details, I can send you a copy of that paper via email. But our model actually automates the selection of which option to choose depending on the characteristics of your power plant and the sites. I'm sorry, I forget what the second question was.
For secondary types of second generation non-food based biomass that can actually be converted. Yeah.
there's actually another paper. I can send you both of my papers then. There's another one which I illustrate how this can be done on a large scale, simply by, it's proportional essentially to the amount of waste biomass the country produces or an island produces. So you could do this by just an inventory of how much straw is going unused, or in some cases just being burned in the fields, becoming biochar, not intentionally, but some of it could actually happen that way. So you could estimate it that way. There may be, in some places, there may be land constraints because you can only put so much biochar in your soil before it becomes saturated and becomes infertile. So part of the equation there would be how much biomass do you have in terms of supply, but part of the equation would be how much land do you have where you can put the biochar, and how much can you apply before you saturate the soil. So do send me an email. I'll send you a couple of papers on those topics.
So the next question comes from Wilfredo Ditan. I think one of the problems to sustain biomass as fuel in the Philippines is the collection and logistics. Whether there's a system or if there are private companies or LGUs who have organized the proper collection of industrial waste or biomass, transport them to the power plants or other plants which require fuel. Have you made a study in the Philippines on how this can be achieved?
The studies we do are, first of all, we try to approach this with an export mindset. When we do a study, we want universal principles. And I talk about my research team at DLSU. We want universal principles that can apply to the Philippines, to China, to India, and such. So we don't want geographic restrictions on the scope of our work. But that said, the paper I showed about distributed biomass utilization actually provides a partial solution to the issue. See, the problem with biomass is it comes from farms and plantations, and it's distributed over a wide geographic area. And what you need is, if you have a large power plant of say 100, 200 megawatts or more, you're going to need large quantities of biomass, and you would need to consolidate all of the distributed biomass so that you have enough to run your plant. And there is furthermore the problem of variations in supply, maybe fluctuations in quality when you have the rainy season. So those are problems. And in fact, the concept I showed earlier defrays some of the risks involved, because rather than needing large quantities of biomass at a single site where you have a large power plant, if you need smaller quantities in different power plants distributed across a broader region, then you're not as sensitive to supply chain risks. If, for example, due to the maybe excess rainfall in a particular period, you don't have adequate supply of dry biomass, then there's a lot less financial risk for the companies involved. If they're still running primarily on coal with some biomass, they can always switch off that option. Whereas if you had one large power plant that relies only on biomass, it would be a major financial crisis for that company if they had to shut down because they had no fuel supply for a few weeks or a few months. So distributed risk is one of the strategies that we can employ.
Thanks for that. So there's a comment by Maximo Aton. Maybe you can add on to it. So maybe what we need to do is to choose the right species that can generate the highest biomass ton per hectare per year. It will be more efficient for land use. Yeah, can you comment on that comment?
That's a great point, of course. The production of biomass and the production of potential carbon neutral energy is a function of having fast growing species, which would have a small land footprint. But we have to be careful because in the papers I showed earlier, which was talking about reforestation, the issue of water footprint also comes into play, because you could have a fast growing species of trees that you're cultivating for biomass production, but you may have water footprint problems, because if you neglect a particular aspect, you may be just transferring environmental burden from land footprint and maybe incurring in exchange for that water footprint. In other words, drying up the surrounding regions, or you could have a phosphorus, nitrogen footprints with their own environmental implications. So it is essential when we look at problems like this that you have a balanced scorecard so that you're assessing your potential solutions while avoiding unintended consequences that were neglected during the assessment.
Well, it seems like you're reading the, the questions from the chat box because the next question is related to your response. So the next question comes from Heriberto Cabeza. So thank you so much for a tour de force of engineering the reduction of carbon emissions. Have you looked at reforestation as a means to sequester carbon from the atmosphere?
Good morning, Alberto, or good evening, rather. Actually, I haven't done it myself, but I've read plenty of work on this. And as I said, there was a paper published 2 years ago by a pretty strong team of researchers. They estimate 200 gigatons of potential reforestation potential for carbon drawdown. It's 200 billion tons, requiring 1 billion hectares of land. But there were some critics who pointed out that's not going to work because you're going to have a water footprint incurred, which we're not going to be able to pay because that water is needed for food production and so on. So the critics were pointing out exactly what I said, that one team was looking at just land footprint, but they were actually neglecting to look at other sustainability dimensions. So I do think that that's what scientific discourse is all about, that people need to be open to criticism because, again, you may think of your baby as the most beautiful in the world, but the other parents might think otherwise. And same thing with science.
Okay, thanks for that. So the next one comes from Patrick Abulancia. So thank you for your great talk. Have you looked at the effects of different sources of the biochar? Would one source be better than the other in sequestration, or do they all perform similarly?
Offhand, I would say, thanks, good evening, Patrick. Good evening from the Philippines. Offhand, my general response for biomass is we go for the low-hanging fruit, and that is waste biomass that is being produced already as a byproduct of growing crops. So, for example, when you grow rice or when you grow sugarcane or oil palm, there is already waste biomass because only a small portion of plants that we cultivate is actually edible. A lot of that is inedible biomass, which is just stockpiled or burned in the fields. So that is low-hanging fruit, and there's tons and tons of that available in different parts of the world. So I would rather begin with utilizing waste biomass to begin with before we even begin to incur extra footprint of cultivating biomass and incurring the land, water, nutrient footprint of actually growing biomass for energy production and for carbon sequestration. Okay, start with what's already there as an underutilized resource.
Okay, thanks for that. The next one comes from Biswajit from South Korea. It is really a very nice presentation with several pieces of evidences of outcomes based on the country-based studies. However, I have one concern that all these mathematical models with biochar and others are possible with linear programming, as the reference contains the linear models with the tool Lingo. However, I will surely start this area of research, and today I really learned a lot.
Thanks very much. Actually, offline, I'd be happy to discuss potential collaboration. I know you're in Korea right now, so that's something we could discuss in the future. We work a lot with a certain class of programs called linear or mixed integer linear programs. Sorry for the non-specialists in the audience. Just because essentially the linearity assumptions involve a trade-off between the model fidelity, how accurately does the model reflect reality, versus model tractability, how easily can you solve the models. And we believe that the trade-off, the research group philosophy is that there are many instances where the linearity assumptions, even though you're incurring some error, are justified by the computational gains that you can run the models, as long as you understand that these are not absolutely perfect representations of reality, but simplified versions of reality. You can calculate the solutions much faster without computational issues.
Okay, thank you. The next question comes from Anthony. So this is a short list of good byproduct used under circular economy principle. However, byproducts use has their respective competition in various technological choices to attain higher value adding alternatives. Where do you rank your approach among existing technological choices?
Well, I think strictly speaking, in my opinion, biochar is much closer to actual implementation because it's actually based on ancient agricultural practice, which we can talk about later on. But the point is, it's not too different from adding compost to soil. Biochar can be like a soil conditioner. It's organic. Of course, it's partially industrially processed. It's also organic in the sense that that's biomass, which originally was in the soil to begin with. So that is scalable. Enhanced weathering is a bit more problematic in the sense that there is almost universal consensus that it's going to be much, much more expensive than biochar production. I would say that mineral application to soil is being done in limited cases, not for carbon drawdown, but for pH adjustment. If the soil is too acidic, typically people would you could lime the soil by putting powdered limestone to raise the pH, but that's very limited in scale. And doing it with basalt or doing it with silicates is a bit different. It's a bit more expensive, but in terms of physical sealing, again, there's a consensus that you can draw down so much more carbon, several times the amount using enhanced weathering compared to biochar. So the physical limit is higher, but unfortunately, the cost per ton of carbon dioxide is also much higher. So there's a trade-off, and that is still a developing debate. But thank you for that question.
Oh, the next one comes from Maximo Aton. So there are several biomass technologies. Which one is more efficient, or which ones would be more efficient?
Well, this really, it depends on how you would define efficiency. If your efficiency definition is based on electricity generation, there'd be a different answer. If your goal is primarily carbon sequestration, there'd be a different answer. So I'd request you to be a bit more specific as to what perspective are you taking for biomass use? Is it, for example, perhaps I can give a very specific example. About 10 or 15 years ago, there was actually a global biofuel boom. I did plenty of research on liquid biofuels based on biomass, where you would grow crops and eventually your end product would be something like biodiesel or ethanol, which you would use for motor vehicles, which it turns out that is actually a lot less efficient than taking your biomass and using it in a power plant to generate electricity, because you'd have fewer conversion steps along the way. If you take the process chain, it actually makes a lot more sense if you were to do this via the electricity production chain.
Thanks for that. The next one comes from Huane Chua. So in the Philippine setting, I've seen that the planned projects of San Miguel Corporation, in which they decided to install battery storage structures all over the Philippines, in particular the new airport construction in Bulacan, to show their shift from coal to renewable energy as a main source of energy. Is this really a sustainable project, in your opinion, to reduce carbon emissions, as battery needs energy to be produced as well?
Thank you for that question. And I know, of course, you have your own special interest in batteries. We look forward to your thesis defense next month. But this is, part of it is technology hedging. We do know that renewable energy is a growing market. And we also do know that when you have renewables, say wind farms or solar farms, then you'd have fluctuating electricity production, which needs to be balanced out with some kind of storage system. So that technology is rapidly developing, and what companies essentially need to do is they need to make bets. They need to hedge their bets and say, let's get into this particular technology at this point in time, because unfortunately, if you wait for certainty, by the time you come into the game, it'll be too late and you'd have competitors already ahead of you in the market. So I see this as a firm essentially making a calculated wager as to how much renewable energy as a global market is going to penetrate the Philippines in the future. And I do think, in the same way that I think perhaps within my lifetime, we're going to have an influx of electric cars, I would bet on that. and the revamping of the vehicle fleet in the Philippines and major parts of the world, I think the same thing is going to happen in renewable energy. And you just have to hedge your bets as a large company that if you want that to be part of your future business portfolio, you want to be a first mover.
Yeah, thanks for that. So the next one comes from Jason Ongpeng. So biochar is a very interesting topic. Are there any companies with pyrolysis equipment in Luzon that have strong ties with DLSU Manila to explore potential research collaboration, for example, in application to civil engineering, such as the production of concrete?
I'm not aware of any specifically, except for those that manufacture activated carbon, which is, of course, it's a specialty product in the sense that it's not a bulk product. It's more a specialty chemical, allied chemical product. And then, of course, as you know, production of char in the Philippines for barbecue purposes is really a cottage industry rather than highly industrialized. So I'm not aware of any.
Thank you for that. Added input from Sipi David, and please, you may comment on what Sipi has indicated here. So, added input on weathering. The Philippines has one of the highest weathering rates in the world because of high temperature and precipitation. Furthermore, we have rocks called ultramafic rocks, which have 3 times the sequestration potential of basalts. In the process, we produce hyperalkaline springs, which we find in Palawan, Pangasinan, and Zambales. Would you like to comment on that?
Yes. Firstly, thank you to my colleague, CP, former executive director of Assured at VOST. I actually learned about enhanced weathering about 11 or 12 years ago from a geologist friend. I wonder if he's in the room, Kaloy Arcilia. I didn't understand what he was talking about a decade ago, but I understand now that, the Philippines being positioned in the ring of fire, the whole archipelago is made either of igneous rocks like basalt or rocks like limestone, which are deposits from marine biota. And you're correct in pointing out that we have even more basic rocks and minerals which would have higher capture capacity than basalt on a per kilogram basis. So I think those should be examined as well. I would be happy to work with geologist colleagues in the future about scaling these up. At the same time, these other rocks that potentially could be used for carbon sequestration are not as abundant as basalt. So it's a matter of mixing up what's available and what can be mined or quarried economically. The problem with enhanced weathering essentially is from the business perspective. If I mine, and I'll stick with basalt because that's a commercial product. If I mine basalt and sell it to people who make concrete or people who make asphalt pavement, then there's an actual revenue stream, which is obvious. If I were to take basalt and grind it down to a dust, so it's actually much more expensive than gravel, and apply it to soil, there is as yet no economic model, or there's no economic or business model because there's no driving force for carbon sequestration. All you would do is, hypothetically, for example, we could take that strip of Manila Bay between the cultural center of the Philippines on one hand and the US Embassy at the north end. And you could propose, for example, this could be hypothetically a test site for enhanced weathering. And you could take basalt and grind it down to maybe not quite powder size because you just need to match the beach sand grains. So maybe the fineness of table salt. And then you would take your gray basalt and lay it down along that strip of sand, because then wave action would actually induce carbon sequestration via enhanced weathering. Except if I were to propose that, I would have people bashing me on social media for perhaps uglifying that strip of Manila Bay. But that would actually work for carbon sequestration purposes, except that instead of having the white dolomite sand beach that we have, you would have ugly gray, but actually eco-friendly, but still not very aesthetic beachfront in Manila. So that's an example of the various aspects, social, economic, regulatory, which will be part of the drawdown ecosystem in the future.
Okay, thanks. We have so many other questions. The next one comes from Crispian now. So, have we, and if not, how can we have these good models integrated into national climate change action plans to achieve measurable results? And as a follow up, how are the government agencies applying these relevant studies?
All right. Well, my philosophy as a researcher is get the ideas and the results, number one, quality assured, so that I put my name on something which has gone through a reasonable quality assurance process. So it's quite likely to be correct. And then get it published so it's essentially preserved for posterity and disseminated throughout the entire world. Because first of all, the atmosphere does not have national boundaries. And the reason that needs to be disseminated to a global audience is if somebody in China or in India or in the US takes some of these findings and implements carbon drawdown, there are no national boundaries in the atmosphere. Any reductions that occur on any part of this planet, some of the benefits accrue to the Philippines by virtue of the reduced climate change impacts. But in terms of how these can be used in the Philippines, I think firstly, our research group in the LSU puts a premium on scientific process, the quality assurance and dissemination, which I think also builds our credibility. But at the same time, we don't really push the agenda so much of trying to, if we're asked for help, we'd be happy to help, but certainly we're not going to push any specific agenda. The job of the researcher is to discover and disseminate. If regulators come and ask for our help, we would be perfectly qualified with the proper credentials to comment on what can be done, but we're not the decision makers. We're just the specialists.
Thanks for that. The next one comes from Dina Schiller. So, in your estimate, how many more years will it take for the Philippines to have a biochar facility?
I think if there was, I'll go back first to the point I made earlier, that countries like Japan, UK, the EU states, China, they decided by a particular year in the not too distant future, we will have zero emissions. Now, that should be where reckoning begins. So I'm waiting essentially for when the Philippine government, on behalf of the Philippine citizenry, would say, let us as a country commit to zero emissions or near zero emissions by a particular point in time. Once a political decision is made, then I consider the stopwatch as running. And I would say, I think in the case of biochar, definitely once that kind of regime exists, within 5 or 10 years, you would easily, this is not high tech. The reason it's scalable in the developing country is it does not rely on exotic technology. Everybody knows how to make charcoal. Everybody knows how to put compost in soil. So it's a matter of within a few years after a political decision is made for zero or near zero emissions, that can be scaled up rapidly in an agricultural country like the Philippines. Enhanced weathering may take a bit longer. I'd say maybe over a decade before that can be scaled up.
Yeah, I think it leads off to our next question from Micah Habok. So, is the support of the Philippine government to using NETs in the future very promising? Or is there a need to further encourage the use of this technology in the country?
All right, well, again, first point I want to make, and this is because this is something that needs to be understood by a climate change audience. It doesn't matter where the carbon emissions reduction takes place. Every ton of carbon removed from the atmosphere, whether you do it in China or the US or Mexico or what have you, benefits everyone on the planet in a distributed way. So the carbon drawdown need not occur in the Philippines for the Philippines to benefit because there are no boundaries in the atmosphere. What I think the Philippines might need to do as a rapidly, we're actually a lower middle income economy. So it's essential for us to have the mindset of middle income economy, that in solidarity with the rest of the world, dealing with a planetary condition and not a national condition, we need to make a similar commitment on greenhouse gas emissions, a serious one that we say everyone else is doing this, maybe not to the extent that China or Japan or the EU would do it, but let's show that we're in this, we're on the same planet, breathing the same atmosphere. So We need to show solidarity in that respect and try to gain benefits. And back to my earlier point, I'm sorry to keep returning to this point, but I think Philippine researchers and in general Philippine or developing country researchers need to assume an export mindset. Our ideas should be good enough, not just for our countries, but for the entire planet. And it's only, and especially in a debate like climate change, there is only one atmosphere. And I think let's drill down on that particular point, drive it into our minds, into the minds of our students. Our ideas should be good enough for the rest of the world.
Yeah, thanks for that. So the next question comes from Wilfredo Ditan. Is there an ultimate analysis and ash analysis of biochar? What is the heating value of this fuel compared with coal, natural gas, or biomass? Does it still have chlorine content? For chlorine, we have concerns on chlorine-induced corrosion at superheater section of the boiler at elevated temperatures. So we have to properly design the heating surfaces of the boiler or limit the stream temperature outlet of the boiler.
Yes, thank you for that point. First of all, I'm not actually advocating the use of biochar as fuel. So heating value of the biochar is a moot point. We want that to stay in solid form in the soil so that we've sequestered the carbon. And typically, of course, you'd have, depending on moisture content for the raw biomass, you're looking at 14 to 18 megajoules per kilogram of the raw biomass coming in. And you'd have to select the biomass type. Again, I understand your point about chlorine, for example, if you're getting this from coconut plantations and such. So there also needs to be an issue on what are the various potential contaminants that would be bad for the soil or bad for your power plant. And in fact, you speak of heat transfer surfaces. The rule of thumb of 10% for heat transfer surfaces or for co-firing is really based on that. By not putting in too much biomass into your combustion system, what you're burning is still mostly coal. So the composition would still be very much similar to what the plant was originally built for. Once you start getting to 10, 20, 30%, you're going to have problems with heat transfer in your plant. And of course, deposition on the heat transfer surfaces from the biomass, slagging is what it's called. And eventually you'd have to deal with major technical issues in your plant. That said, I'll say two more things about this topic. And then again, with apologies to the non-specialist audience, we can discuss offline in more detail. Number one, my PhD student, a former PhD student, Dr. Belmonte of UST, actually in her final PhD paper, wrote up essentially calibrating the pyrolysis conditions so that you're making sure to match the biochar composition and potential contaminants to what your destination requires. So that's one point. I can send you a copy of that paper as well privately if you want details on this. Another one which I did not do, but which I read about last year, which might be a major breakthrough if it can be commercialized, is synthetic coal. I read a paper in Science last year where some researchers in the US developed a process to make biocoal, or synthetic coal, which is a biomass-based product that chemically and physically is almost indistinguishable from coal that comes from the ground. And this is important because what that means is, unlike biomass, if it physically or chemically resembles coal, you could get to 100% displacement. In other words, you could tune that kind of a process potentially so that a coal-fired power plant, or a plant that was originally built to run on coal that comes from the ground, could potentially be run for the rest of its operating life on synthetic coal, which is actually based on biomass. But that remains to be seen how long it'll take to commercialize such a process. Maybe that's at least a decade away from fruition, but at least the initial breakthrough has been made.
Thanks for that.
Thank you for those detailed questions.
Yeah. So we have actually two requests for collaboration. So for the audience who are who want to get contact details of Dr. Tan. So I'll be sending everyone a copy of the presentation which was presented here, and I'm sure that Dr. Tan will include his email at the end of that particular presentation. So as he mentioned earlier, if you have any additional questions after we complete this webinar, please feel free to send him an email. Okay, but we still have a few more questions to to go through.
Well, I guess we can go until 9:30 or so.
Yeah, okay. So we'll end everything by 9:30. So for some questions that I might not be able to tackle or to ask, please feel free to email Dr. Tan. So the next one comes from Dina Schiller. It's more of a comment. So their company partners with some organizations such as TerraPass, in which they purchase carbon credits to offset some of our greenhouse gas emissions. So the biochar systems seem to be a good potential to provide significant carbon offset. Okay, thank you for that. Yeah.
Thanks for that. May I just respond briefly? I have a tendency to respond with very long monologues, but I'll try to cut down on that. As I mentioned early in my talk, the default scenario, at least in the Philippines, seems to be tree planting or reforestation, which is a good part of the mix. But I think we can use our imaginations to look at alternatives. And for as long as you're careful about biochar application, in other words, you have a properly tuned, not a backyard style production system, but production of biochar where you can minimize dioxins that would be created during combustion under suboptimal conditions. You can avoid that if you're doing it properly in an industrial setting. As I said, putting biochar in soil is conceptually not too different from putting compost in soil. And the business model for it could be soil conditioning. You're improving soil conditions, but at the same time, you're having carbon credits that are occurring by virtue of the soil application. And again, a quick plug for my former student, Dr. Bea Belmonte of UST is quite our local in the Philippines, expert on this. So you may wish to contact her about some of those details.
She's actually in the audience. Yeah, Dr. Bea is in the audience. Okay, thanks for that. So the next one comes from Brother Francis. How can Sahelian countries contribute to reducing carbon dioxide emissions? Do you have a comment on that?
Thank you for that, brother. I understand it's quite late or extremely early in the morning for you, but thanks for staying up. I think for any given country, there are actually in the negative emissions technologies spectrum, there are different techniques that would be applicable in different countries. So for example, those that are heavily agricultural would benefit from things like, as I said, biochar application, but there are other techniques and some of these are more exotic than others. Enhanced weathering, I think, is a bit problematic in dry climates because you need that rainfall to dissolve the rocks that you apply to soil. So in arid countries that would not work, but there are other techniques that might. And I think, for example, well, let me give an example. One of the technologies being developed now, which is relatively exotic, is known as direct air capture or DAC. Direct air capture is essentially, it's a physical process or physical/chemical process for drawing down carbon dioxide gas from the atmosphere, almost like you have a synthetic tree. I think that's a good way to describe it. It's like you build a plant, industrial plant, which actually functions a bit like a biological plant that photosynthesizes. So this skims the carbon dioxide from the atmosphere, and there is plenty of research being done on this, but I think it might be deployed in more developed countries. The technology is a lot more exotic. Unlike these two that I mentioned, these are all based on existing mature technologies that you can switch on within a couple of years in a developing country very rapidly. Thank you for your question, but maybe final point. I think I like your point about questioning how these things can be done in different countries. I mentioned solidarity. This is a global cause to fight climate change. I think everybody who can contribute, even developing countries, should attempt to contribute.
Okay, thanks for that. So the next question comes from Lawrence Bello. So he is working on phytoremediation, and bamboo has shown potential in remediating heavy metals for soil. My question is, bamboo is a fast-growing, low water footprint and good carbon sink plant. Can the bamboos be used for will the bamboos used for remediation be good for biochar?
For the context that I'm describing right now, absolutely not. Because the point now is, it's a two-step point. Number one is, while biomass captures carbon dioxide, the biomass itself will rot if left, say, lying on the ground. So eventually the same carbon that it photosynthesized out of the air will return to the atmosphere unless you find a way to lock it up somehow. So then that's where biochar comes in, because if you carbonize it, it's a lot more stable. It will last for centuries. If you take a piece of charcoal and leave it for decades on, after a few decades, it will still be charcoal. So that's the purpose of decarbonization. The problem is, if you do this, the very same heavy metals that you extracted from the soil via the growth of the plant, if you carbonize that, those heavy metals are still in the biochar that you created. So if you put that in soil, you're just closing the loop in a bad way on the heavy metals. So I think that's certainly an incompatible set of technologies and solutions.
Thanks
Thanks
for
for the
that.
question.
Yeah. So the next one comes from Ming Lang Tseng. So he'd like to know your thoughts about the drought that's happening in Taiwan with regards to carbon emissions and climate change. Can you comment on that, please?
Thank you very much. First of all, perhaps when I see you next year in Taiwan, I'll give a live talk on this. Yeah, I think one of the climate aspects that Taiwan is experiencing now, it's a clear illustration of how climate affects what we call, we actually have a recent paper on this, which has yet to be submitted, but will be submitted within a few hours, on what we coined the term complex island economies. These are economies like a country like Taiwan or Singapore. If you go to Europe, a country like Republic of Ireland, which are small islands, therefore they're geographically constrained, but they're not like small island developing states like, for instance, the Micronesian states, which are very simple economies that subsist on agriculture or tourism or some combination of these. So we're talking about geographically confined islands like Taiwan, but nevertheless, these islands are actually like scale models of entire large countries in contiguous land masses. In other words, if you look at Taiwan, there's agriculture, there's energy production via different, there's coal production, there's renewables, highly industrialized with semiconductor production and various other complex industries. And parts of the Philippines are actually like that. I would argue that if you take Luzon as it fits the same description of a complex island economy. Now, that's enough of the introductory response. What I actually meant to say is that there needs to be a balance between two things. Climate change mitigation, meaning what should your country or city or region do to draw down CO2? Do you switch to more renewables? Do you implement negative emissions technologies? But the second and difficult part of the balancing act is you need climate change adaptation. Because like it or not, as I speak, as we discuss, climate change is already occurring because we have all those greenhouse gases already in the atmosphere. So as we try to draw down carbon, we should also be thinking at the same time, what are the things that are going to happen due to climate change in the coming years or decades? And it's going to have unstoppable momentum, or almost unstoppable, to make sure that it's not going to disrupt our way of life. And for example, Taiwan may be having problems with renewable energy. So that's an issue of renewable energy portfolio being vulnerable. This happened in the Philippines a little bit less than a decade ago. It happened in California in the US several years ago, where they had significant, both of these regions, Mindanao and the Philippines, and California in the US have substantial hydroelectricity. So when a drought hits, when you have a multi-year drought and you have dropping water levels behind your dams, you're going to have power outages. So to begin with, you had a clean energy source in hydroelectricity. But at the same time, these same technologies that we need to fight climate change might themselves be vulnerable to climate change. So how do you break this impasse? Well, there is going to be a cognitive overload for the human mind, even for specialists. This is where computer models come into the picture. They can be, they're not, the way I do it, it's not artificial intelligence, it's really intelligence enhancement. You give cognitive aids for human decision makers so that they can make smarter decisions. So thank you for that question. See you in Taiwan maybe a year from now or less.
Okay, thanks for that. So the next question comes from Paolo Gabriel. So it's not directly related, but what is your opinion on the role of solar energy in terms of contributing to the zero footprint goal by 2030?
Oh, it's actually very related. So thank you for that point. Solar definitely is a rapidly growing industry. Solar energy will be part of the mix. It's a matter of matching energy choices that we make with particular locations. So for instance, I've heard of discussions of putting large solar farms in the Sahara Desert or near the Sahara Desert, and to export some of that electricity just a few hundred kilometers north, a few thousand kilometers north to Europe. So that's an example of matching, because you obviously have plenty of sunshine in the Sahara Desert. And not too far from there, you have a huge energy sink in Europe and North Africa. So potentially that kind of large scale planning could be part of the mix, but you certainly don't put too much of the reliance on solar energy. You wouldn't do it, for example, in Finland, where you'd have darkness for half the year. So that's a good example. And likewise with wind, likewise with hydroelectricity. I think it's a matter of trying to look at the big picture. What are your choices? What are the geographic and climatic conditions in your location that would restrict the use of renewables or various carbon drawdown techniques?
Okay, thanks for that. So I guess I'm down to the last question. This one is from Marilyn Francisco. So can you provide a good reference material, which she can refer to and study on upstream waste management, such as on gasification and pyrolysis?
I'm sorry, say that again, please. I missed the first part of the question.
Okay, if you can provide a reference material, is there something that you can recommend that would be good material to study on upstream waste management for gasification and pyrolysis?
Interesting. Thank you for that. First of all, nothing comes to mind immediately because I don't do research on solid waste management. But again, if you send me an email, I can find some potential promising resources for you and send you a link which you may use. But it's not something which comes to mind automatically to me. I'll try to help where I can.
Okay, so I think that's all for the questions. Thank you very much, Dr. Tan, for answering all of these questions. And like I mentioned, I'll be sharing the presentation to you guys, as well as the link to the recording of our YouTube. But before we go, I'd just like to inform everyone of our next talk. So, like I mentioned, the sustainability lecture series is done on a monthly basis. So, next month, we are scheduled on May 26th. That's a Wednesday, same time, 8 to 9 in the morning. And we'll have J. Michael Haboneta, who is the managing director of the Nexus Innovations Lab of De La Salle, Lipa. He will talk about his lessons from the Yellow Boat Foundation experience. So if you're interested to join us next month, so please register at bit.ly/DLSU05, or you can scan the QR code over here and it will take you directly to the registration page. Okay, that's it. Thank you guys for joining us this morning. Have a great day ahead for those of you who are in the US or somewhere else. Please enjoy the evening and have a good night. Thank you, guys.
Thank you all. Thank you, Raymond.
Thank you to the team.
Thank you, Kay. See you in the next lecture. Thank you, brothers.
Brother Francois, Brother Joe, good to see both of you.